Am I audible?
Yes, yes.
Okay. A warm good afternoon to all after an interim of a month. I would like to repeat the major instructions regarding to the webinar for the sake of newly joined participants after Vernaton told. Switch off your mics and cameras unless you have to express something to us or till we invite you. And most predominantly, even if you rejoin after leaving the meet, don't press the present screen button because if you do so, there's a possibility of losing the presentation of the speaker temporarily. And we wish you to pin the presentation screen of speaker by tapping it from the people list. So it will be easy for you to see the slides of our speaker. And the chat box is only for asking your queries for the Q&A sessions. And all kinds of discussions using chat box are strictly prohibited due to the decision made by the webinar committee. Discussions can be done in our WhatsApp group called Cosmos, and there are a lot of WhatsApp platforms for the UL Space Club like Sky Safari, which is started a month back. So if you are interested in that, please DM to Vernat and he'll provide his number in the chat box soon. So those are the informations and the instructions related to today's webinar. The time is 3 and 4. Shall sir, can I move to the formal introduction?
Yes, yes, sure, sure.
Okay, sir. Once again, a warm good afternoon to all. I cordially invite all the veteran scientists, teachers, UL Space Club organizers, students, and all other participants to the 34th session of UL Space Club's webinar series. We, the UL Space Club, is a foundation under the umbrella of Uralungal Labour Cooperative Society, stands for enriching and flourishing the scientific aptitude of students, especially in space field. Within a short time span of 3 years, we conducted many great offline events before the COVID. And exactly in May 2020, in the context of the pandemic era, we began this new journey called the webinar series. And it's going incredibly well for the past 10 months. Like I said, we are meeting here after an interim of 1 month in this monthly webinar platform, even though we met on 28th February on the occasion of National Science Day. Anyway, let me move to the official obligations which have assigned to me. Today, in the 34th session, we have Ms. Nandini Harinath as the lead speaker on the topic Odyssey to the Red Planet. For me, there are many fortuitous things related to this webinar. When 4 days back, I visited our Kutisa's home with my friends of UL Space Club. He handed me a book entitled as India's Rise as a Space Power, which was written by the great U.R. Rao. Not only that, I was surprised on the next day when I came to know you are all born on that day, March 10, from a Google Doodle which honored him. The degree of excitement reached at zenith after seeing the poster that our guest is from an organization named after him. Yes, today we have an expert who is the head of Mission Planning and Analysis Division 2 at UR Rao Satellite Center, Bengaluru under ISRO, with us to explain all those matters related to the mission operations. She was a part of most of the important satellite missions scrutinizing, if I am allowed to say so. As we seen in the poster, we are going to hear the anecdotes of a lady who was a major part of the Mars Orbiter mission, Mangalyaan. Like I mentioned in the write-up of this webinar, that real-life Martian mission of India only fetched less than the make-believe Hollywood film Gravity. There are a lot of planning gone on the purpose, design, and working model of this mission. Not only this, but in the each and every satellite that goes to the space from here. It's our privilege to have you here, ma'am. I gladly welcome you to the 34th session of UL Space Club webinar series. Namaste, Nandini, ma'am.
Namaste.
Uh, Thank you. And after that, we have all core team members of webinar committee here to give you the instructions when it's necessary. And our moderator is, as usual, Shajil sir, the one who controlling and developing our platform in each and every session. And he will gonna introduce our respected speaker. Our chief mentor, Ike Kutisa, the former director of ISRO, is the backbone of the whole activities of Space Club, is here with us. The whole webinar family, including the eminent scientists all over India, will be with us in this session too. And then, like our Varnatan mentioned, A student fellow of UL Space Club is here, who was the best student of National Space Camp conducted at Bengaluru, and also one of the very few, actually very rare kind of student who also get the direct invitation of ISRO chairman to see the satellite launch live from the Sriharikota itself. Yes, I excitingly welcome our Abhinandan to handle the Q&A session after the talk. And the one who plays a major role in connecting us to UL, Damodaran sir, is here to express the word of thanks after the session. And right now, this webinar is recording and streaming in YouTube by our member Adil Krishna. All set, it is good to go. So, without any further delays, I invite the moderator, Shajil sir, to take over the session. Welcome, sir.
Hello, sir.
Is there any problem, sir?
Shelter is not there in the list. You may.
Has he left?
Maybe a network connection. Maybe a network issue.
He may have some technical issue, perhaps. Hello, Shajil Marsh. Hello. Looks like he has some.
Yes, sir. He is not in the meeting.
Shelter is there in the meeting.
Okay, Kutti sir, give me a moment. I will call him. Sensor is there, but
Okay. It's a network
he's
issue.
saying he has some network issues, sir. So
Oh,
I
yes,
think
come, yes, come, yes.
Kutti sir,
Yes, sir. There was an
Shajil Marsh has come.
Okay. Thank you, sir. Thank you, sir. I think Sriram has created a room for introducing our guest here, and unfortunately, I met with some technical hitches. That's why I am not able to continue with you. And today we are celebrating the 34th session of this webinar series, and we are nearing to a 1 year when along with the pandemic spread of pandemic, and that 30 is also coming to in a reduced end. We have such an expectation with our scientific community that we are now expecting. Okay. Today we are speaking on Odyssey to the Red Planet, and that red planet is around 38.4 million kilometers away, and that's the thing. And the true journey or saga of our prestigious institution ISRO. And today we have a great scientist from this great institution, Mrs. Nandini Harinath, and she's continuously supporting our students for the past for this great program, and we are expecting the words and her presentation to our students. And she's the scientist G of UR Rao Satellite Center, Bangalore. That's the heart of our great organizations. And when we speak about these red planet, and we have a connection of I have to proudly say the connection of UL Space Club with these things. We have made a drama in the name of Mangalyaan. That was the prestigious attempt, and that is working there in that orbit. And we presented it at University of Calicut 3 years back, and all our students and the entire team under the guidance of Kutti sir, we have done it, and we keep those moments as a glory of our UL Space Club. And this also remembers that great event, that's the simple event we have made. And today we have Nandini Harinath ma'am with us, and she's the mission director of planning and analysis division, UR Rao Satellite Center, Bangalore, and being the mission director for Resource Sat 2A, that's a Earth observation satellite, and Resource 2B,
It seems, Varun, it seems Shajil Marsh has problem, technical problem. I think again he is off the screen.
Yes, sir. Yes, sir.
Why don't we save the time by requesting Nandini Madam to start the program, and then Shajil Marsh can join his role uh, before the question answer session. Is that okay, Varun?
Yes, sir. I think it's okay, sir. Shall sir,
Then you please
I don't
invite,
have a
please,
problem.
please invite Nandini Madam.
Okay, sir. Thank you for the opportunity, and really glad opportunity for me. And Sriram had made a good room, and Shail sir also introduced a little bit about Nandini ma'am, and we are very glad to have you here, ma'am. And all of us are excited and awaited to hear from you. So you are welcome to UL's Space Club webinar session 34, and we are ready to listen you, ma'am. Or to you.
Yeah. Thank you so much, Varun, and thank you, Kuti sir, for giving me this opportunity. It's always exciting to talk to students, especially the elite ones that you have in your club. It gives a kind of a positive energy, even while preparing, and you think of the students and the kind of questions they'll ask. And students these days are really smart, and I'm honored to be talking to you and all of you. And I'm especially happy today to see PJ Bhatt sir, who was my boss while he was in URL Satellite Center. I've worked with him for so many years. I feel really honored that he is attending this session today. And Parama sir and all the seniors who are there from ISRO, Murli, welcome to you also. And my hi to all the children and the students. I hope not to disappoint you today. Basically, Katti sir, when he spoke to me first, wanted me to speak on
Okay.
mission planning, design, and operations. So I work in mission planning analysis division. I'm a hardcore mission person for the last 25, now 26 years. That, of course, is my favorite topic. But then I thought, why speak only about mission? Why not speak about the Mangalyaan mission also? The Mangalyaan is always it churns up excitement in most people, because it was, I think, the first time people actually followed any satellite mission so closely, and entire world, media, students, people all around were following the activities on day to day. And of course, there have been a lot of books, movies, Bollywood, Hollywood, all kinds of stories. I'm sure most of you know most of the things, but still to hear from it, from a mission perspective, or from somebody who's actually worked on it, I thought I could give you maybe few little details which you probably don't know and probably will find it exciting. So the first part of my talk is going to be on mission planning and analysis, or the mission design itself. And then I would lead from there, I would lead to the Mangalyaan mission. So, what do you mean by mission? Many times all of us use this word mission and satellite interchangeably. So, what is actually the difference between a mission and a satellite? So, like for example, if your mother sends you to the market to get a packet of milk, you're on a mission. Or if you think that you're going to climb a mountain on a Sunday and go for a trek, you're on a mission. So it's a journey basically. A mission is a journey which you perform for a specific reason. So when we actually associate a function to the satellite, we call it as a mission. So now that you know the first word, the mission, very clearly, let's move on to our topic. Today, I'm going to speak a little bit about the design, mission design. and how we start planning, taken off from the design, and then how the planning leads to mission operations, and then on the Mangalyaan mission. So all of you, I mean, you could, I don't want it to be a monologue, but if you, I don't know the rules of your webinar, but if you do have questions, you can cut me across and ask me. I don't mind taking up questions either way, even if it's in between. I don't want you to go to sleep after a good lunch, especially it's a weekend lunch. So you could just interrupt me anywhere if you want to. So what exactly comes to your mind when you say mission? For me, it would have been the movie I have seen, Apollo 13, when the astronauts say, "Houston, we have a problem." So that is what comes to me when you think of mission and a mission control room. That is what I would have thought when I was your age. Then subsequently, we've had the Mangalyaan mission itself, wherein all of you have got a peep into the mission control room, and you actually seen how the operations take place. So that is not a movie at all. That is a real world. So, but it's no less than a movie. So, what actually happens there is that there are a lot of people sitting and a lot of experts who are running the mission, but the hardcore of the core team in that control center and the one who directs everything that happens there is the mission operations team, and that is where I come from. So, of course, there are a whole lot of people supporting. There are experts from every field who are there who carry out the mission operations. But then the one who controls or interacts with everyone and takes the decision is the mission operations lead. So this is at a higher level, just to tell you what a mission operations is about. You must have also seen the recent Perseverance landing on the Mars surface. The crater was called Jezero crater. So I'm sure all of you have seen that live or maybe the recorded video. So there exactly, again, you got a good glimpse of what happens in a mission control room or what happens in the control center and how the activities take place. So, so moving on, let me just show you about a little bit about the kind of work we do in mission. So basically, if you look at the outer circle, we are the kind of people, what you call as jack of all and master of none. We need to know about, we are basically system people. So we need to know about every system that is there in the satellite. We need to interact with each and every agency that ISRO has a collaboration with. And we are the people who actually bridge the spacecraft to the end goal. So if you look at the outer circle, you will find that at the top is the ISRO management, people who get us funds and people who decide that this is the mission that is to be done, and they are the ones who get us the programs. And then adjacent to that, you can see the user community. You have, so you have, you have different kinds of users for every mission. So you could have users who are using the data, maybe it's a remote sensing satellite. You have people from the agriculture department or from the defense forces, or you could have, the whole lot of satellite applications that you have. You have the communication satellite, you have transponders. So you have this now the new and the most important application, that is the navigation. So you have this entire community. In fact, each and every person, in fact, it actually boils down to every person who is actually in our country will be using this navigation data sometime or the other. Nobody really steps out of our houses without GPS, isn't it? So navigation is not just for, earlier on it used to be for big aircrafts and ships. Now every person who goes on any roads, in fact, not only Bangalore roads, requires navigation. So these are the users again. And then, so what I was trying to say is mission per se, a mission person has to interact with all the users to know how they're going to be using the data. We need to be building interfaces to give them the data the way they want. And then coming down to the side, the arrows, we of course need to be, that's at the top level. At the more working level, we need to be interacting with the launch vehicle team. We will be interacting with the people in the launch site. Then of course is the project system and the subsystems. So basically, in order to carry out the operations, we would need to know how exactly the systems are built, and it is all done together. So we will be interacting with the designers of each and every system and taking their help in carrying out the operations. And off late, in fact, we've had a lot of international collaboration. So we've had payloads from NASA, ESA, JAXA, everywhere. So most space organizations across the world, we've had some kind of collaboration with them or other. So so we constantly interact with them. And then the last bullet in the outer layer is the control center. So the pictures that you see in the newspapers, the pictures that you see on TV is mostly of the control center. We have the state-of-the-art control center, but let me tell you, I have visited the NASA control center also at JPL. What we have is better than most control centers that I've seen. So we interact with the engineers and scientists at the control center, and in fact we from the mission team will be carrying out the operations in what we call as a commissioning phase, just as the spacecraft is launched, but for regular mission operations are taken care by people in the control center. So this is the outer layer. Now coming a little bit to the inner layer, that you see the light green circle, that's the detailing about the work that we carry out, right from telemetry, telecommand, the commissioning, the payload operations. The payload operation is basically the very reason the satellite is flown is for the payload, and in order to operate the payload and get the data. So the commissioning of all these, and also the regular operations design is also done by us. And the last bullet that you see is the graveyard or re-entry. So I'm sure all of you are familiar with space debris now. It is one of the hot topics in space. Everyone is talking about how to get rid of space debris and how the satellites that are there are obscuring the view of the astronomers, and how it's going to cause problems to other satellites. And we also get a threat of collision with this debris. The collision threat could be with live satellites or with debris. So all this, taking care of all this is also done by our team. And eventually, when the satellite is declared that it is no longer usable, it is either sent to a graveyard orbit or it is made to re-enter. So of late, there have been a lot of international laws wherein you cannot just keep the satellites in space forever. So while you're launching, you have to tell what is your plan for re-entry or decommissioning. So we in the mission team have to work out how we are going to re-enter the satellite, or what is the proposal for that? Do we have enough fuel for that? How do we passivate the system? How do you deactivate the battery? So these are some of the things that we normally take care of in the mission. So let me just, this is a little bit more technical. I'll just give you a very brief idea about what exactly do you mean by mission design. So broadly, I need to make a statement. Mission statement is something that tells you about the goals and rationale for carrying out the mission. Like I said, a mission is something which always has a specific function associated to it. So if I have a mission, somebody needs to tell me, okay, we need a mission to look at the country, or to, you need it for surveillance. So that could be a broad mission goal. Or you need a satellite to look at the oceans. You need a satellite to monitor the weather. So these is a broad mission statement. And from there, you will define the mission objective. So mission statement is a very broad statement. From there, you derive how exactly do you work for the mission, or you make a quantitative estimate. So what are the requirements for this mission? And then you go on to characterize the mission. So you define, okay, what kind of orbit do you want to fly it in, what kind of systems that you want to carry, what should be the weight of the satellite, who should be the users, who should be the ground segment. So you start characterizing the mission. And then eventually, everything is about a trade-off, isn't it? You cannot get the best things without a cost. So you have to weigh the cost versus what is your utility. So you need to do a kind of an evaluation, and which is a continuous process. So we call that as a mission evaluation. We look at it and say, is it really worth doing it the way we are doing? What is the implication on schedule? What is the implication on the technology that we have? So, there's no point having a satellite or designing a satellite which requires so much technology that you don't have right now, and you have to wait for years to develop the technology. So you need to somewhere evaluate what is possible and what is the cost. And finally, having done all this, we work out something called the mission requirements. So there comes the design of the spacecraft. So when you say a requirement, so you will be telling, this mission has to carry this kind of a payload. Maybe it's an optical payload, it's a radar payload, or it's a telescope, or it's a very high resolution camera. So there the requirements will be drawn. What would be the kind of payload, how much power it will require, what is the type of controllability that the satellite demands. So those requirements will be drawn. So all this together is the kind of work we do, and this is what is called as the mission design. Okay, so yeah, so I just wanted to show you a kind of, this is a animation of a satellite in a polar orbit. I've kind of accelerated it when it's not over Indian region, and you can see that this is a sun synchronous orbit, and the satellite is going from South Pole to North Pole. The reason why I put this up is, when I said a broad mission requirement, if there is a mission requirement to cover the entire globe, okay? So if I have to cover or take images or map the entire globe, I should be needing a satellite which goes from pole to pole. So obviously, we have something called the polar sun synchronous satellites. You must have heard about them from the previous speakers. So if the broad statement is to get a global coverage, I would need an orbit which is going from pole to pole. Now, this is, and how it covers pole to pole is, the orbit is going from the South Pole to the North Pole in the ascending node, whereas the Earth underneath is rotating, and that's how you will cover the entire area. Now, let us say the requirement is to cover only the Indian region and not to look at the pole, or not to look at the entire Earth. So if I have a satellite like this, I would be obviously wasting a lot of time going over the poles. So I would then, I would then try to design a constellation which is with an orbit or an inclination, so that the satellite stays on our country or our region for most of the time. So we call them as inclined orbit. So so what you can see from here is, so basically, this is again depends on the main objective of the mission. So what exactly do you want from the mission? Okay, so let's move on. Yeah, so there were a few things that I thought I will tell you before I go to the Mangalyaan mission. So let's say that one of the main important things that we do is the mission analysis. In fact, our work starts from the time that the satellite is actually conceived. Right from the time the program is sanctioned and then the project team is formed and people start working on the satellite, our work in mission starts. So it's not just about, the final stage where you see, mission planning and operations. It is right from the time the satellite is conceived. So you can see that we do lots of analysis. The mission team, including the flight dynamics team, decides on what kind of orbit we should fly in. That's the example what I showed you just now, whether I need an inclined orbit or I need a sun synchronous orbit or I need a different type of orbit altogether. What kind of sensors are required and how do I mount the sensors? How do I place the antennas? How do I place the solar panels? How do I carry out, whether there is enough energy, the power system supports all the mission scenarios. So these are typically what we do. So I just wanted to show you one example of the analysis that is very, very commonly done in our missions. We fly something called the star sensors, which is used for the attitude. So basically, star sensors look at stars and tell you the position of the orientation of the satellite. The orientation in terms of the X, Y, Z axis, which we define in our satellite terminology as your roll pitch. How it is aligned with respect to a frame, a reference frame, is what we call as the attitude of the spacecraft. So the star sensors will tell you how exactly this axis that you see, how the body or the satellite body is oriented. But then there are some very, stringent constraints that the star sensor poses on us. The star sensor per se should not see the sun. It is meant to see the stars. So, but then it cannot also see the earth, because the earth, as you know, has it has albedo and it reflects 30% of the light back. So the star sensor has to be mounted, or it has to be used in such a way that neither should it see the sun nor should it see the earth. So basically what here we are trying to do is we are trying to find out whether in all the mission scenarios, whether the way we have mounted the star sensor, whether it clears the sun and the earth, and whether it is able to see all the stars the way it is meant to. So this is typically just an example of what the kind of analysis we do. The other analysis is we decide what kind of a launch window you have. So what time of the day you should launch, and what kind of orbit you should launch in, how much fuel are you going to load, and what is the fuel budget for the entire mission? How much are you going to consume just to stay in orbit? How much are you going to consume if you have a contingency? So all this, how much of fuel do you want for deorbit? Nowadays, deorbiting is also a very important factor. So all this life estimation and analysis is also again done by the mission team. So in fact, I could go on and on, but let me just tell you the few other things. As a just point which I would like to explain is the payload data. So if you're carrying a camera, so how are you going to operate the camera? Who is going to be receiving the data? And how the data is going to be disseminated after it is received on the ground. This entire plan for the ground segment is also done by the mission team. So this is one of our other major jobs that we have. So, okay, so let me move on. So this is typically, I just thought I'd show you few important aspects of few of our missions. This is NISAR. I don't know how many of you have heard of NISAR. The full form is NASA ISRO Synthetic Aperture Radar. It has a very stringent requirement on the orbit. So what you see here is a diamond, right? You can see the diamond in the middle of the slide. Yeah, where I put an arrow. So you can see this diamond. So the stringent requirement is that if you imagine this diamond to be a tube around the Earth, the requirement is that the satellite should be within the tube throughout its lifetime. So if the satellite is going to be there for 5 years, it should remain within this tube all the time. So it cannot deviate from, we call it as a reference path. So there is a reference track, and it should not deviate 300 meters. Here we're talking of meters, 300 meters in the width and then 250 meters in the width actually, and 300 meters in the height. So it should remain within the tube, and then the mission team has to plan for frequent maneuvers and taking account of all kinds of disturbances, the decay. We need to ensure that the satellite stays in this tube. So this is one typical example of the work we do. Now coming to the planning, so all that I described was the kind of analysis we do. Now all that analysis goes into what is called the planning. So why do you need to plan? I mean, anything that you do in your life, you have to plan. If you have to celebrate something at home, or if you have a function going on, nothing goes on without a good plan. So we do exactly the same thing. So for us, the big day is the launch and the initial few days after the launch. So they are the most important days for us. So for that day, that is the launch and the launch plus 7 days, 7 days, whatever is to happen, we start planning for it almost 4 years in advance, or right from the time the mission is conceived. So all the planning is for that one day and for the next few days about how we start turning on the systems and how we commission the satellite. So this planning requires knowledge of the satellite elements and interfaces of each of these elements, and interfaces of the satellite and the ground systems. So finally, after we've done all the plan, is what results into what we call as the mission operations. So these mission operations is what you actually see on TV, that what you see in the control center. So, but then there's a lot of work that has gone, planning, design, analysis, that has gone much before it reaches the stage of the operation. So here, even to carry out the operation, there's a whole lot of documentation, whole lot of simulations that are carried out. So for one single day of the launch, we do a zillion simulations to ensure that that day goes by properly. So the simulation is just not for the onboard satellite elements, but also for the ground elements. So the ground elements, right from something as trivial as a system, a number of systems, the networking, the ground stations, the interfaces between the ground stations and the software. And there's an entire host of software that needs to be working very well for us to receive the data and interpret the satellite data and display it. So all these elements are, we carry out number of simulations, and we test all of these systems to make sure that the mission operations carry out, they go as per the clockwise precision. So now, not just now what I talked about was pre-launch and launch. It's just not just about that, but also we need to take care of contingencies. So for every plan that we have, there is a plan B and plan C and probably plan D. So there are number of contingency worked out for each and every operation that we carried out. There are backup plans. And all these plans are so well documented, and anytime anything happens, they get automatically executed. So post all of this, of course, is the performance of the satellite, and that analysis is also carried out by our team. So essentially, to put everything in a nutshell, mission per se, the analysis that you heard till now, the analysis, the planning, the operations, is essentially a teamwork. And it is not something that can be done by a handful of people. It is an entire big team. And the most important thing about this team is every person in the team has to play his role to perfection in order to get a successful mission. So teamwork makes dream work. So that is the absolute core, and that is the point I want to emphasize, especially for you students. I'm sure when you organize this webinar also, you would have realized how important it is to be a team player, how important it is to coordinate and make sure that everybody does their, performs their function perfectly. So yeah. So now I think I spent almost Yeah, okay, 40 minutes now. I'll try to move on quickly to, I'll skip this. Let us move on to Mangalyaan mission per se. So this is some of the satellite operations that I wanted to show how this is a communication satellite, wherein we are not able to go into the geostationary orbit directly, but then we do number of burns and how the orbit is eventually we go into a geostationary orbit, a final orbit. And while this is happening, different activities take place, like you have calibrations of the sensor, deployment of many of these mechanisms. So all these are also part of mission operations. So this is another important, a very nice sequence that I wanted to show. This is for the NISAR again, how, the NISAR has a 9-meter boom and a 12-meter antenna. This is, of course, in collaboration with JPL, and this is a very important mission for ISRO. It is going to be launched in 2023 now. It was 2022. It has gone to 2023 January after the COVID. This is a very interesting mission because this, Murli is here, and he will understand how complex the mechanism is to release a 9-meter boom with a 12-meter antenna. It could be as big as the antenna is probably bigger than most of our drawing rooms. So this is done in a span of 4 days, and every activity that happens and every command for every orbit is documented, planned, simulated, and discussed almost 3 to 4 years in advance. And that is the kind of preparation that goes on into these kind of missions. Yeah, so this is typically to show you, we have something called the sequence of events. We plan how the activities take place from day 1 to say day 30 or day 35, and it includes everything, changing of the orbit, controlling the satellite, how we commission different elements, how the network stations come and go. So all this put together is what we call as a mission timeline. So let me just, this is, Pijabat sir is here. I wanted to show this mission, especially, is called the Space Capsule Recovery Experiment. I'm sure none of you have heard of this, but you must have all been kids and babies when this mission took place. This was 2007. This was one of the first and the most prestigious missions and a different mission that ISRO did. This is kind of a precursor to the human space program, wherein we launched a satellite and then we kept it in orbit for 13 days. And the satellite per se, the entire satellite, in an integrated way, a functional satellite was recovered in our waters in Bay of Bengal. And this is the picture that you see. The challenging part here was, we have sent a lot of satellites to space. So our PSLV, or the launch vehicle, it's a trusted workhorse which repeatedly does it successfully. But we never had brought back a full satellite, an integrated satellite, a functional satellite anytime. So this was way back in 2007, wherein the satellite fired, we call it as a deboost maneuver. The satellite fires in its retro rockets, decelerates, and then enters the atmosphere. So the challenging part here in the mission was to survive the atmospheric re-entry. When the satellite enters or anything enters the atmosphere, a huge amount of friction is created, which causes a lot of thermal heating. So the external surface would experience something like 2000 to 3000 degrees centigrade. So if the satellite has to survive that kind of a temperature, it should have a very strong thermal protection system. So this satellite had the silica tiles, and it had a special nose, which it survived. And really will tell you, I mean, I don't have the time today, but maybe sometime later. It is nothing less than a drama. So this had a very, very nice story. It was not all success all the time, but eventually all that well ends well. We had recovered the satellite, and you can see these are real pictures that you see of the satellite after it re-entered. There was this is the flotation system which kept the satellite afloat in the sea, and then you can see that there is a recovery team which went and towed the satellite back to the coast. So yeah, so this is something, one of the very, very nice missions that we did. Yeah. Now coming to Mangalyaan, which is, let me just look at the time. Yeah. I have about another 15-20 minutes, right?
Madam, you are free to go. Now it is only the 3:48:49. You can go up to 4:15, madam, or
Yeah.
even
Okay.
beyond. We have no problem.
Yeah.
Because we began a bit late, so you can please go. You can complete your task. Complete your task. No
Yeah.
problem.
So yeah, this is about, we had satellites going to Mars, right from Mariner 9 to Mangalyaan, and now the latest one is the Perseverance. So most of you have seen the videos, I'm sure, of the live landing. And why Mars? Is it, Mars is the most alluring planet that we have. It looks like it is very, very far. The distance varies from, say, 225 million kilometers to 400 million kilometers. Though we're talking of millions of kilometers, but if you look at it on a cosmic scale, it is still very near. So, and moreover, the red, we call it as a red planet. This blood-like hue that it has a great potential that we suspect maybe it could have sustained life. So Mars especially has intrigued mankind for thousands and thousands of years. So obviously, you would not, when we say cosmic scale and it is very near, it is one of this most challenging things is to go and actually look out. And to, then it was then ISRO decided that, like most of the missions, let us also go and find, and more because of the science, and also to prove that you have a capability for an interplanetary mission. One of these things that Carl Sagan says always reminds most people working on this mission. He had said that our long-time survival is at stake. It's our responsibility to ensure that our species survives. For that, you have to it's not just survival of the mankind, but mankind to survive forever. So with all these dwindling resources that you have on the earth, so that's one possible thing. Not maybe, some generations from now, there is not enough space to live. We might have to start exploring, places to live. So, though Carl Sagan romanticized that idea, but right now what you hear from Elon Musk is that he's going to put up a colony in Mars very soon. So this is not really now a story. It's going to be more of a reality now. To have a colony in Mars, and I'm sure before 2030, I'm sure you're going to have a man to land on Mars. So, but now having said that, ISRO also decided to take a plunge and go ahead with the Mars mission. One of the biggest spin-offs that I see, is that the way the mission went, it was just and the kind of awareness it created, especially for the young Indians. I'm sure it stirred up all their interest in engineering and astronomy. You could, many times when I've spoken to students and teachers across universities and colleges, especially the Mars mission, seems to have tingled all their interest. So there are so many people now actually following up on missions and who want to do engineering and astronomy after having read and seen the success of this mission. Maybe, the next generation, maybe one of you attending this webinar, maybe spearheading a mission to Mars, Venus, or Jupiter, or maybe even the remotest asteroid, who knows. So Mars touched the human imagination like no other planet. Why? Because Mars has so many similarities with the Earth. One straight similarity is that Mars and Earth have almost the same length of the day. So length of the day is almost 24 hours even in Mars. But then Mars, being the outer planet, takes much longer to go around the sun, and because it's the outer planet, it gets only 44% of the sunlight. But then the similarity ends there. They are actually very, very strikingly different. If you read about Perseverance, and if you read about even the Chinese missions that have gone to Mars, so the basic objective of all these missions is to know, how Mars has preserved its history, how atmosphere, whether Mars had water and whether Mars had life at all. So why most people want to know about Mars is they think that by knowing about Mars, maybe we'll know something about the Earth also. So because Earth hasn't preserved its history, whereas Mars seems to have preserved what has happened. So to get a first-hand information about what are the kind of things that are available on the surface, what is the surface made of, might answer some of the questions. And of course, there's always the doubt, or there's always this $1 million question that everybody asks: are we alone? Are we the only human beings or the living things in this Milky Way galaxy? Is there somebody somewhere maybe in this galaxy or some other galaxy, asking the same questions like us and trying to explore and go to different planets and galaxies? So these are some of the things most people are curious about. So then after ISRO decided that it was time to do the Mars mission, the story began. There is, I'm sure all of you have heard about the launch window constraint. I have 2 slides on the launch window constraint. I'm sorry if it is repetitive, but then, this launch window constraint was the one that really drove us to race against time. So most people say that ISRO did the mission in 18 months. From the time of project approval to launch. Of course, there was a study team and there had been some background work done, but having got the sanction and money and the realization of the project happened in 18 months. But why was it only 18 months? So that was basically because there was a launch window constraint, and then if we had missed the window, we would have had to pay a very heavy penalty in terms of fuel, and again, we would have to wait a couple of years. So that is why this big rush to do it in the 18 months, wherein the geometry was most optimal and it was the most favorable condition. And then having said that, this was our first interplanetary mission. So what is an interplanetary mission? Why did you not call other missions as interplanetary? I'll just explain to you in a while why it is called an interplanetary mission. And there were, of course, lots and lots of challenges. First of all, to develop hardware to survive in the Martian environment was itself a challenge. And the deep space communication, communicating with the satellite through this gamut of radiation, that again was a big challenge. And another big challenge was the navigation, because the path the satellite had to take had to be very, very, very precise and very well known, and what kind of accuracy that we required. And in order to know how accurate you were on your path, you needed to know your position and velocity at every instant very precisely. So to develop the technology and to develop that, the process of finding out or navigating through the trajectory, that was one other very big challenge in this mission. And then the last and the most important, of course, is the mission planning and management. How did we actually plan, and how did we plan and execute this mission is something that I'm going to be talking about. Okay, so how was this mission management done? So, like I said, there were three main aspects to this mission design: navigation, the trajectory of the satellite itself, and then testing it in all its scenarios. So, one is to build the hardware, thinking that it should work in the scenario. Another thing is to test it out, in the most realistic scenario as possible. Because once you launch the satellite, and then you encounter problem, you cannot have a situation wherein your design is not sufficient to cater to your needs, especially when it's an interplanetary mission and you don't have prior experience. This becomes extremely important because it's the first time you're actually doing it, and the only way to get it right is to test it a zillion times on the ground, and to imagine and to design for each and every scenario that you might encounter. So that in itself was one of the most challenging parts of this mission. So then I'll talk a little bit of what kind of mission management autonomy we had in this mission. That is coming up in the next few slides. But then how did we actually do it? Because it was our first mission and we did not have any experience. So one of the things was, this was to learn from the previous missions and to learn by our own experience. It's always, they say that failures are, much more important than success, because you learn a lot from failure than you learn from success. So it's always important not only learn from your failures, but it's also important to learn from other people's failures. So this is where we had done a thorough analysis of, why and how the other missions to Mars had failed. And then it was thoroughly discussed and debated, and we had to ensure that we did not make the same mistakes again. So, and we had our own experiences with our own satellites, and we knew the things that could go wrong. So all these things had to be taken care. And then another important thing was we tried to use a lot of heritage technology, so that, especially when you're using some totally new element which you have never tried in space before, because space is an unforgiving environment. So if you have not tested something out before, if you have not flown some element before, it's really a big risk to do it for the first time, and that too in a critical mission wherein a lot of things, the whole mission is going to depend on that particular element. So what was done was a lot of re-engineering and innovativeness was brought into the mission. And there was clear-cut planning and coordination within various teams, be it with the hardware team, the communication team, the navigation team. And then there is this capability that ISRO has. I think this is something very, very special to ISRO, the capability to get up for unplanned events and to find site solutions on the fly. So obviously, like it happens in our real life, nothing goes as per plan 100%. We all agree and we all know that very well. So even though you planned very well and all that I described about analysis, planning, years and years of planning, it doesn't really ensure that everything goes 100% right. So there is an element of surprise always in every mission, and that's what makes it exciting. So to get up for that and to find solutions on the fly was our strength. So this was one of the most important things, and the reason why the mission was successful. Yeah, now coming to a little bit of science. How did the mission design start? The mission design started with this unique trajectory. I'm sure all of you have seen this Mangalyaan movie. You must have read a lot of books. You must have seen a lot of YouTube videos. But of course, they're all okay. Most of it is probably right. So, but then to think of it, when you say an interplanetary mission, this was the first time an object made by ISRO or by India had left the sphere of influence of Earth. Now, what do you mean by sphere of influence? Sphere of influence, when the satellite is close to a celestial body and the gravitational forces of other planets can be neglected, you can say that the satellite is within the sphere of influence of that celestial body. So once the gravitational force of that celestial body. If you need to go out of that, you need to give something called the escape velocity. So all of us have read this in our maybe high school. So the region inside which the approximation is valid is called the sphere of influence. Now, if the satellite is not inside the sphere of influence of the planet, then it is considered to be around in an orbit around the sun. Now, this is the famous trajectory diagram. I'm sure all of you have seen everywhere. There is the inner circle, the white circle, which is the inner orbit of the Earth, and then there is an outer circle, which is the outer orbit of Mars. Now, basically, the problem is to go from the inner circle to the outer circle. So what we need to do is to convert a very complex 4-body problem into a 2-body problem. So how did we convert it? How did this patch conic method work? So before I go to that, I just wanted to show you a little bit about the different sphere of influence and in terms of distance for the various planets. The Earth's sphere of influence is 145 times the radius of Earth. And this is extremely large compared to the size of the Earth. So if you have to go out of the sphere of influence of the Earth, you need to give that extra small bit of energy or what we call as a hyperbolic excess velocity for the spacecraft to leave the sphere of influence of the Earth. Now, I'm sure all of you have read conic sections in, I don't know if it's taught in 9th, 10th, or 11th, maybe 11th and 12th in college. But then, you know, when I did conic sections in my school, I had no idea how and where it was used. But of course, I knew ellipse is E0 and hyperbola, what happens, and then a circle, what happens. Sorry, ellipse E is less than 1 and E0 is a circle. So all this we knew, but we really didn't know the importance of all this till I actually did the Mars mission. And these, the eccentricity factor or this becomes extremely critical when you're designing a trajectory. Something that looks so trivial, like the eccentricity of a conic section, can play such an important role in an interplanetary orbit transfer, is something that you would probably realize when you actually design this. So here we followed something called the Hohmann transfer. So I'll just take 5 minutes because it's something very interesting, because all of you read conic sections. I thought I should put this forward. So if I have to go from one planet's sphere of influence to other planet's sphere of influence, so what would I do? So if I give that little bit of extra or hyperbolic excess velocity, so I get into a trajectory which is a hyperbola. At that instance, what you see here is the inner planet, and then you see that, so this becomes a hyperbola. So but it is a hyperbola for this particular around the Earth, but if you look at it, it goes into an orbit around the sun. But then it would have become a hyperbola for the capture or the planet where you want to get captured to. But then you don't want it to remain a hyperbola and go elsewhere. So you want to capture it around the planet. So then you need to decelerate here and then reduce the eccentricity to a value less than 1, so that you become a ellipse around that particular planet. So this is basically the concept that is used here. So how exactly does this work? So when I said a launch window, so what exactly did I mean when I say we had a launch window of 18 months? So I don't know if you've seen this calculation before, but this is very simple basic mathematics. So the distance between the sun and earth is what you call as 1 Armstrong, right? 1 AU. So all of you know this. So this is how the distance is measured. So if the distance between the earth and the sun is 1 AU, then the distance between the sun and Mars has to be 1.5 AU. So this Hohmann said, if I have to go from one orbit to the other, the easiest and the most optimal transfer, optimal in terms of fuel, not optimal in terms of time, but optimal in terms of fuel, would be to go in a Hohmann transfer. That is, I go into an orbit around the sun and then intersect the orbit of Mars appropriately. It's more like a rendezvous problem. So now, if I have to do this kind of a transfer between an inner orbit to an outer orbit, what is that I have to do? So I have to, if you look at this distance is 1 AU, and this distance between Sun and Mars is 1.5 AU. So this total distance for this orbit, which is our transfer orbit, is 2.5 AU by 2. So the semi-major axis of this kind of an orbit becomes 1.25 AU. So if you look at, by Kepler's laws, if I have an ellipse of a semi-major axis equivalent to 1.25 AU, then you apply the Kepler formula and you will get the time taken to travel this distance from here to here is about 0.7 years. But we also know that Mars takes 1.88 years, because Mars is an outer planet. It takes much longer than the Earth itself. So it almost takes twice the number of days. So it takes roughly about 1.88 years to go around itself. So if Mars has to move, so if I have to, the satellite moves 0.7, takes 0.7 years to move from this point to point here, then the Mars probably will move only 134 degree. So if Mars moves 134 degree, then the Mars has to be 46 degree ahead of Earth at the time of departure. So this is what creates or dictates our launch window. So every time we have this opportunity that Mars is ahead of, see, both these are moving at different speeds, right? So this geometry will come only at certain time. So when Earth and Mars make an angle of 46 degree, that is the time if you launch, then by the time Mars takes 0.7 years to move 134 degree, the spacecraft would have taken the 0.7 years to move from here to here. So that is where the time when the possible time where the spacecraft can have a rendezvous with Mars. So once they have a rendezvous, the satellite and the Mars, then it's a question of firing thrusters to get captured around Mars. So this is one of some basic concept of how we had arrived at the launch window. Now moving on from there, so once there was a launch window that was decided and the geometry was found, so we didn't have a launch vehicle which had the capability to give us that hyperbolic, the escape velocity straight away. Whereas if you see, NASA had launched Maven, and Maven was put into a trans-Mars trajectory straight away. But we did not have that capability in our own launch vehicle. So we had to fire thrusters every time that we came close to the Earth or at the perigee point, and we kept on increasing this apogee distance. And at one point of time, the burn which was most critical, what we call as a trans-Mars insertion burn, there was just enough velocity provided for the satellite to set off in this cruise trajectory or towards Mars. So at that point of time, it had attained this extra velocity and went towards Mars. But then it is not just about giving the velocity, right? It is also about giving it in a perfect direction. So both the magnitude, so you saw it is more of a rendezvous problem. So you have to know the time Mars takes to reach there. The satellite has to have exactly that perfect velocity to reach the point where Mars would reach, because that intersection happens only once at one point, and it will not intersect ever again. So it has to be very precise, not only in direction, but also in magnitude. That is what made this burn very, very, very critical. So it is like, you're trying to target a pill box, which is something like, a 50 by 50 kilometer pill box from a distance of about 225 million kilometers. So it is like hitting a dartboard. Like a lot of people give this example. Where you play dartboard, right? And you hit the bullseye. So the dartboard is in your room, but here the dartboard is actually across the world. It's on the other side of the world. If you scale it up, and you still have to hit the bullseye. And why you have to hit the bullseye? Because if you don't, you will not be going anywhere close to Mars. So this was the kind of error only that we could tolerate, and for this is where we required this extremely precise navigation techniques. Most of you have read and heard about Doppler. In fact, the traffic police uses Doppler most of the time to know if you're over speeding on the road. So this is one of the most common methods of sending a signal, receiving it back, and then noting the change in frequency. That tells you exactly both the position and velocity. This is one of the very, very precise methods of knowing a spacecraft's position and velocity. But here in this, that was not really sufficient. So there was something called the delta DOR, which is again a very, very, very technical and a very good technology in which the satellite actually, one would actually look at the quasars and then relative to the quasars determine the position of the satellite. So this technology was used here, and then that is how the imaginative trajectory that you are seeing, it is very, very essential that the spacecraft stays in this trajectory throughout this travel time, and that 0.7 years is roughly what we call as 9 months travel time. And during this entire 9 months, we have to stay on track. And then if you did deviate, you would have to do small corrections to get back on track. So we kept on doing this trajectory correction maneuvers. And then finally, you must have all heard about the Mars orbit insertion. While we approached Mars, again, to change your trajectory from a hyperbolic trajectory to get into an elliptical orbit around Mars, we had to do the deboost burns, wherein we reduce the velocity, applied brakes to get captured around Mars or get into the sphere of influence of Mars. So, but that was not the only challenge. The other challenge, there were lots of many challenges. Now, the biggest challenge was the communication delay. When you say 225 million kilometers, imagine I'm having this conversation with you and I'm talking to you and you hear me after 20 minutes. And then you ask me a question and I hear your question after 20 minutes. Then I give a reply and you hear that after 20 minutes. Imagine what kind of conversation we would have. So this is something very, very similar that would happen when you actually try to operate the Mars orbiter mission from Earth, because with the speed of light, that's the speed at which our signal travels, it takes about 22 minutes to reach the satellite. But then that is not the only hurdle. There are so many other problems that come. All these, the objects themselves are constantly in motion. I mean, they're all dynamic. The sun is moving, the Earth is moving, the Mars is moving, a satellite is moving around Mars. So all of them constantly in motion around the sun can also cause us a lot of problems. And then you need to receive this signal through this gamut of radiation. That's the other big challenge. So there can be some geometries like what I'm showing you. This is called the blackout geometry, wherein because the Earth is the inner planet and the Mars is outer planet, there can be instances where Mars and Earth are exactly opposite to the sun and they all are in a line. So what would happen is when you send a command or you need to receive telemetry from the satellite, that is from Mars to Earth, it has to pass through the sun. And if they're all aligned, one is the sun can physically obscure. That is one possibility. The other possibility is it has to pass through this high, dense, ionized atmosphere, and there is a possibility that we don't get the signal when this geometry occurs. The other interesting geometry is what we call as a whiteout, wherein the Earth, being the inner planet, comes between the Mars and the sun. So when this geometry occurs, even though the Mars is on the other side, because you have a big glaring object right behind you, the sun, that also causes problem. So it is not just, sun when it is in the middle, but sun is like having, if there was a big focused light behind my back, you would obviously not see my face. So something similar happens. It's just not about seeing the satellite, but it's about receiving and having the capability to communicate to the satellite. So this also causes a problem. So there are instances for days together you will not be able to communicate with the satellite. Then what do you do? So the other things that can happen is by the design of the orbit, the satellite itself goes behind Mars. Like the orbit is such that between the Earth and the Mars itself, the Mars itself is obscuring the satellite. We call it as an occultation. And then there were some instances wherein we had to switch off the antenna and the related elements for certain periods in the day. That is more to save on the power. So those instances also, we do not know what is happening to the satellite. And whenever, the satellite had to take pictures of the Mars, or it had to make orientation changes, it could stop communicating to us. So apart from the blackout and whiteout, there were many instances wherein we did not have, or we could not communicate to the satellite. So now what is the baseline solution? When you are not able to communicate to the satellite, what exactly can happen? So one thing that can happen is, if something is going wrong, you do not know what is going wrong, and then how do you set it right? So the best thing is to, have everything, the satellite to behave autonomously, have all the features built within the satellite itself, so that the onboard, both in terms of hardware and software, it takes care of itself totally. So it's like, 15 days the satellite is on its own. If there is any fault in any of the systems, the satellite itself will identify that fault within itself, and then it will take subsequently a recovery action. And the recovery action also, it executes on its own. So at any given point of time, the satellite is able to take care of itself totally. So this was a kind of both onboard software and hardware that we had built in to take care of this. In fact, this actually is required for any interplanetary mission. So most of these missions, you will find that you will have to build a great deal of autonomy, because it's almost impossible to micromanage. It's impractical to micromanage the satellite from the Earth. Yeah. So this is again a very, very, like I said, expect the unexpected. There was a comet siding spring which came from the Oort cloud outside the solar system, and this just happened to come close to Mars just after our Mars orbit insertion. And then we had to, we got an opportunity to take pictures of the comet. It was a once in a lifetime opportunity. And also we had to protect ourselves and the satellite from the comet shower. So this was something that wasn't really expected, but came as a surprise. But it was a good thing because we were able to capture a few pictures. We had a color camera, by the way. So we had to reorient the camera towards the comet shower, and that was also challenging because the comet itself was moving at a very high speed, almost say 7 times faster than the satellite itself. So we had to get a very, very accurate position of the comet at that point of time, made sure it had favorable geometry, illumination, and not obscured by or glared by the sun. And we were able to take some pictures. Yeah, so I just wanted to tell you that, okay, the Mars orbiter mission still continues to give good data even today. We've collected some really good pictures. Probably the science and the application team has done a mapping of the entire surface by now. And even today, we are operating it, operating the camera. Recently, I'm sure you saw it on the ISRO website. We got an opportunity to come close to Phobos. We had captured some pictures of Phobos. This was pretty much recent, I think 2-3 months back. So Yeah, so though the mission was planned for only 6 months, the mission really outlived much beyond what was expected. Basically, because the hardware behaved extremely well, much better than what we expected, and there were no failures that really led to the end of mission criteria. So that is the reason it's still giving us, it's alive and giving us data. Yeah, so you heard about most of the other achievements too. Yeah. So this is one of the few pictures, very rare actually, taken by any satellite. The Mars orbital mission itself, we did not have enough fuel to get into an orbit very close to the Mars surface. So at one end, we were almost 80,000 kilometers away from Mars, the apogee. But then that was really not a wasted thing, because that gave us an opportunity to get the entire Mars disk in one camera frame. So our camera was almost 5 degree by 5 degree field of view, and then we could capture this entire Mars disk in that camera frame. So it actually proved to be a blessing that at one end we were able to go that far and get this. And in fact, this picture, I think, got us the Times Award, because no one had got this entire disk in one frame earlier. Most pictures that you see of the Mars disk are all collated and stitched images. So this is one frame. And this color camera had red, green, and blue colors, and these are some of the pictures that that were available like early in the mission. And this was the first. This was again a very thoughtful, let's say, proposition by the team. The proof of the pudding is in the eating, they say, right? So when everybody on TV says, yeah, you successfully got captured around Mars, and then we are now orbiting Mars. So what is the real proof? The real proof is to take a picture of the Mars surface and say, yeah, we are there. So this was, just 40 minutes after the Mars orbit insertion. The excitement had still not died down, but this event was pre-programmed, luckily, before the Mars orbit insertion itself. We had time tagged this event, and just after the burn got over, and the spacecraft had reoriented, and we had got the telemetry data, the camera started clicking pictures of the Mars surface, and within an hour we had received all these pictures in our control center. This is one of the first pictures, and really sentimental one, a really good one, especially. So Mars is, of course, home to a lot of volcanoes. In fact, the highest volcano in the solar system is in Mars. So we had got an opportunity to image this volcano. It's called Olympus Mons. And these are some of the valleys and craters that our camera had seen. And this is just another crater. And yeah, thank you so much. I don't know if I exceeded time. Sorry about that. Yeah. So with that, I end my presentation. Yeah, this was another memorable moment where the head of state came, and it was very motivating for all of us. Of course, we were nervous, but then it was a great moment that he was there to support us at this time. Thank you so much. I can take the questions now.
Thank you.
ma'am. Thank you so much. Chelsea, are you there?
Okay, I am here, and I was not able to join with you because of some technical problem with my part and connectivity. I already now only I could clear it, and it was a great event for our students to see something curious about the Mars and all these things from the mission director of ISRO. And the technical position she is holding is, we know it's so high, and we consider she's proud of India also. And I think we got only 4 lady scientists in this session. 34 sessions we already completed, and we want to honor this great lady of India, and we find a lot of future from her part to this country and to our children. And your words and guidance will make some show some shower of some dreams in their mind, and they will be definitely they will be guided to the next future that we want. And a lot of girls are with us, and I think really you are a great inspiration for our students also to become a scientist or a mission director like you. And we expect some more information from you in future about the Mars. And I already stated that the Mars is the Mangalyaan mission is so hard relation with our students, because they have done a very simple but dramatic thing on these things. And thank you, ma'am. And before we are concluding these things, I want to get familiarized with you from the technical aspect. And I request our Honorable PJ Bhatt sir to say something on the UR Satellite Center and the responsibility of a mission director like that. We want to hear from PJ Bhatt sir on this great office and its importance. PJ Bhatt sir, could you help us?
Sure, sir. Before
Bhatt
that, I
sir?
have a request, sir.
Hello?
Hello.
I think he's
Sure, sir, I have a
available here.
request for
Okay.
that, sir.
Then let's.
Okay,
Then I invite the founder of.
Yes, Shajil, carry on, carry on. Hello.
Sir, I think it's again a network issue, sir. But sir, could sir, before moving to both of you, Shail sir, I have request before moving to them. We couldn't give an introduction about Nandini ma'am, detailed formal introduction about Nandini ma'am to our student because you are having few network issues, so we missed that, and it will be a big loss for us, our students, if they are not knowing who's talking to them. And let me give a formal introduction about.
Yes, then before we start that, we'll get some reflection from PJ Bhatt sir. Varun, please wait for that.
Okay, sir.
And we'll get what is your Rao Satellite Center and what's the things going on here. And we'll get a formal introduction from our PJ Bhatt sir. Bhatt sir, please. Please.
Thank you, Shajil sir. It is an honor for me to speak here about Srimati Nandini and her talk today. I think it is very apt that students here in this Real Space Club got an opportunity to listen from a veteran of mission operations, mission planning and operations area. Nandini, she has covered here about aspects related to mission analysis, design, planning and operations. But in fact, the number of missions for which she has worked, I think it is countless. I can't even list them because so many of remote sensing missions. To start with, so many remote sensing missions, and she has touched upon certain aspects related to overall mission design by mission aspects, but focusing more on Mangalyaan. I'll come to that. But kind of challenges this team has handled with respect to remote sensing operations is huge. Another day you have to get her for learning about those things only, I would say. Today she covered, I really covered the mission analysis, design, planning and operations, the style in which she covered, using examples and explain it in so simple way, knowing very well that the audience contains a good number of students, and utilizing various aspects. She could have told many things, but due to paucity of time, she took some specific things. But all aspects of mission analysis, design, planning and operations she has covered. I was very happy to see her taking very apt examples from SRE. I know SRE TS2 is to her heart. I know that. SRE missions, she would be very proud of about SRE. SRE and NISAR, two characteristic missions. In fact, I would say SRE is, I would term it as a first step towards the human space mission. Okay, so NISAR is the most prestigious mission as on today for ISRO. And both of them, she took such a nice examples and explained today. Thanks to Nandini, I could learn something about NISAR because these are not available in public domain. Okay. She also covered on mission architecture very nicely through that diagram of layered circles. And then she briefly touched upon elements of mission operations. But when coming to Mangalyaan as an example, the way she covered Mangalyaan, I was curious what Nandini is going to talk about Mangalyaan today, because many people know so much about it. But she took mission planning, analysis, design aspects of Mangalyaan and focused on that. And the way she explained launch window, I'm telling you today, her slide, I would love to have that slide with me. So the way she explained that our launch opportunity should be such that when we are exactly Earth, Mars, this angle with respect to this thing should 46 degrees. That she explained it so well. And then the way she described trajectory design of mission from a mission perspective, from the point of view of how you have such a short, such an opportunity which you miss, what happens, and then what are the challenges involved in that, and then autonomy, spacecraft autonomy, all the aspects related to spacecraft autonomy, why spacecraft autonomy for an interplanetary mission for Mars has been covered by her from the point of view of signal delay, communication, interruption, occultation, etc., etc. So many. She briefly mentioned about an opportunity which we got, which was a golden opportunity of observing comet sightings. I just want to add some two, three sentences to that. Very interesting sentence, because we are sitting here after a few days after the birthday of our great mentor, Professor U.R. Rao. Now, this sighting spring created a lot of discussions in Mars mission planning during the planning stage, whether we should take this opportunity or we should go for Mangalyaan after 2 years. There was a lot of discussion here. I remember to have participated in the discussion. The one man who forced and supported us so well, even though we have only 18 months or 16 months, as she told, it was so challenging. One man who supported us, this is an opportunity, we should reach there. And as she mentioned, it is such an opportunity will come after millions of years. So it was such a great support for us, guidance from us, from the great man, Professor U.R. Rao, our Guruji, which made us to go there, and in fact they're observing just after reaching there. It was just a question of few days. After that, we had to do this observation, not only save us from that comet tail, also observe the comet. And it was such an, I know what this mission team has done, so much they have done for the purpose of doing this. And all these things, Nandini covered it so well. And for me, after a long time, listening to Nandini was, I enjoyed it so much. I think UL Space Club should organize more and more talks. There are, I see there are 2-3 more mission specialists sitting here. I see Pramoda Hegde, I see Sundar Murthy. There are people sitting here. I'm sure all these people can give more and more of insight into the mission challenges of various missions. So, Nandini, on behalf of UL Space Club, I belong to UL Space Club. On behalf of UL Space Club, we profusely thank you for this, spending your time and coming here and enlightening all of us about mission planning, design, and operations. First time in US Space Club, the seminar has happened on this topic of ours. We all belong to that discipline, and especially focusing on Mangalyaan. Thank you so much.
Thank you so much, sir. Thank you for your kind words.
Thank you, PJ Bhatt sir. I think it's all these are from your heart, and you are so closely associated with this great organization. That's why we invited you, and we know you are with us. You are continuously supporting these students for the past 5 years. That's a happy thing for us. And let me invite Ike Kuti sir to make his reflection on this talk.
Thank you, Sajal Mash. Today is a very, very special day. As Bhatt said, that the talk today was not only excellent, it is a rich content, wide coverage, and Nandini has done full justice to the topic, to the entire satisfaction of all of us. So I don't know how to express our thanks to you appropriately, but I say a great deal of thanks. And as Bhatt said, we have got a end-to-end picture of what is a mission plan. I know a little bit of it because I had opportunity to sit with your colleagues, your gurus, and your contemporaries during 1990s and 2000 in many discussions and reviews. And what I understood is mission planning is the brain behind the group of mission planning is the brain behind the entire mission. The success, the problems, everything is foreseen in the visionary eye of the mission planning group people, and you belong to that, and you are heading it. You are heading it. So we have got the very right person today too, and I must not only thank Nandini Madam, but also your director, uh, Ms. Uh, Kunji Krishnan, has very kindly agreed with my request to lend few of you, including few women scientists, and what he has given is really a very nice gift in a gold plate. Thank you for that. And today we have a lot of our colleagues, AC Mathur from Ahmedabad, RM Parmar, Ahmedabad, D. Narayana Murthy, our launch vehicle man, PK Sundaramurthy, Murali, who is going to talk on 10th April on mechanism, spacecraft mechanism. He was here. I could see him. And Bandari was there. N. Sundarajan is there. V. Mahadevan. I could see these names there. So they were all listening and enjoying the talk. And the number of listeners remained something like 60. And it's a great day for us. And I thank Nandini Madam so much for taking so much trouble to give such a very, very rich talk in such a simple language with an excellent presentation material. Thank you very much. Thank you.
Thank you,
Thank
good
you
sir.
very much, sir. I'm really overwhelmed. I also thank all my seniors, PJ Bhatt, Mahadevan sir, all of them actually. I've learned a lot from them. We are all here today only because of them.
Uh, Thank you, Kuti sir. And our students are eagerly waiting for the with their questions. And it's time to for that question answer session. That question is Q and session is dealing our Mr. Abhinand. He is also a prodigy from this group, and he is a recipient of Niyas Maya award. Now he is a student at Ramanujan School of Mathematics in Pondicherry University. He fall in love with mathematics, and he want to become part of great science institutions. Welcome, Abhinand, to lead the Q&A session.
Sir,
Abhinand, for one minute.
Okay.
Varun, I think we need not do that job now. I know Varun is trying to talk that we have not done enough justice to Nandini Madam. She has done justice to us. We are not introduced in a very formal way. We did it, so Arun is trying to do that, but then the time is so this thing. Varun, I will uh, apologize, Nandini Madam. Don't worry about it. We'll do it some other time. And I just wanted to say, P.S. Abhinand is a boy who has spent considerable time with Professor U.R. Rao when we had a space camp in Indian Institute of Science campus in 2015-16, I believe. So he is one of our darling in the UL Space Club, and a very, very promising boy, and he is going to coordinate the question and answer session. Abhinand, please come.
Sir, there is an issue. Abhinand Aridhar, he was having few network issue and his phone was having a few errors. So he was asking Ashwati to manage the question answer session. So Abhinand Aridhar, otherwise let's call Ashwati.
Varun, I couldn't see Abhinand now here. He was there. Just 1 minute I could see him. But now
Yes, sir. Yes, sir. He just texted me that his phone having few issues.
there was unexpected connectivity issue. That's also met with
Yes, sir.
me also.
So, sir,
invite Ashwati.
Ashwati will handle the question answer session, sir.
Okay, Harinath, am I audible?
Yes.
Okay. Good afternoon to all.
Ashwati, why don't you put on the camera?
Sorry, sir. My camera has some issues.
No problem. Carry on. No problem.
Okay. Today's session, Odyssey to the Red Planet, was very nice one. We had a very good experience. As this topic is very interesting, so many questions have been raised in the chat box. Can I ask the questions one by one, ma'am?
Yeah, go ahead. Yeah, let me try to see if I can open the chat box. Yeah, you can ask me.
Okay. The first question was, the estimated functioning period of mom was about 6 months, but why it is still working?
Okay. Yeah, so see, when you design a satellite, one of the major design parameters is what is the life we are designing for. So here the life was designed for 6 months, but fortunately what happened was the systems that were designed for 6 months, they have worked much beyond the expectations. And another big constraint for most missions is the fuels, right? Eventually the satellite runs out of fuel and there is no fuel to maintain its orbit, and it would either just drift away or crash land. So here the fuel that was left over, the margin that we had was also sufficient. And fortunately for us, we didn't have to use the fuel for any other purpose, right? So whatever fuel was there, it was slowly getting consumed without having, since it didn't have any other major issues in its lifetime. So that is why it is still working. So basically the hardware worked well, and then there was sufficient margin fuel left. Yeah, next question.
Okay, ma'am. The next question was asked by Atul Sachin. Why is ISRO is not planning to add a rover with Mangalyaan 2? Why is it still named Mars Orbiter Mission and not a rover mission?
Oh, so okay, this is a tough one, right? So there were discussions recently that we should have a landing mission on Mars, but then right now I must say that is not a priority, but there is still discussions. I don't think ISRO has really finalized the Mangalyaan 2 configuration as such. The study team is still looking at all the options, but I must tell you it's not an easy job to land a rover. It is still on the cards. We don't know about it. Yeah.
Okay, ma'am. The next question was asked by Krishnendu TN. The question is, what are the challenges of Mangalyaan 2?
Okay, so Mangalyaan 2 will be a totally different ballgame, right? Mangalyaan 1, the focus was on to reach Mars. So the main objective was to get captured around an orbit around Mars. So that was the primary objective. And then there was not so much focus on getting the science, though we did have payloads. but in terms of apportionment of the payload capability, we did not have a big capability. So with Mangalyaan 2, now reaching Mars should not be the primary objective. The primary objective would be to derive as much science as possible, carry as many payloads as possible, and try to derive science out of it. And that would be the real challenge for Mangalyaan 2. In fact, that is the challenge for most missions. If you look at Perseverance, it landed on a crater, right? Why it landed on the crater? The crater, it's called Jezero or something, Jezero crater. So basically, that was a dried lake. So they expect that there was water there, and that eventually dried up. And by digging and getting samples there, they are very sure they can make out if there was any water, and if there was a possibility of life. So that is the basic intention of most of these missions to various planets, to really find out what is the composition, was there life, any form of life was present. So these are some of the things that even Mangalyaan 2, or if there is a repeat mission or a follow-on mission, that would be the main challenge actually.
Okay, ma'am. And next question was asked by Febin Fisher, one among the brightest students of UL Space Club. What is the conclusion came from the observation of methane sensor in Mangalyaan?
Oh, so the methane sensor, basically, it didn't have, okay, I don't think it really predicted the methane content, but then it had a lot of spin-off results, apart from the methane. It did come up with a lot of analysis and papers on the composition of the atmosphere. There were a lot of international publications also that came up. You can actually look up. But of course, like you said, the methane sensor did not actually find the methane per se. Methane per se, we were not able to find in the limited operations that were carried out.
Okay, ma'am. Next question was also from Adul Sachin. ISRO had to launch the Mangalyaan orbiter in PSLV instead of GSLV. What were the problems that were faced by ISRO during the launch?
So, the PSLV, right, it has a certain amount of capability for weight. It cannot take beyond a certain payload mass. So, that was the reason why it has put us in that orbit wherein we had to do multiple burns. And also compared to GSLV, PSLV was extremely reliable. And in this short time frame, we wanted a very, very reliable launch vehicle, which, had proven. Of course, GSLV is also reliable now. But at that point of time, PSLV was the workhorse, and it would have given us sure shot the orbit that we wanted. So that was the reason that PSLV was chosen. And if you're talking about the challenges, I'm sure you've seen it in the movie. So because when you design an interplanetary trajectory, the departure and how it departs, and that becomes very critical, because it is like I explained, right? When you are exiting, you have to exit with a certain velocity in a certain direction, and it has to be very precise. So that called for a different type of satellite injection, so that the orbit parameter had to be such a way that it was away from the Indian shores. So when you don't have a satellite tracking center to look at your satellite the time the rocket is injects the satellite, so we had to send a ship, and of course there were a lot of issues faced by the ship. to reach in time, and then it was going to the other part of the world. So these were some of the issues. But then PSLV per se did a very good job. It gave us precisely the orbit that we wanted.
Okay, ma'am. The next question was the how close we to colonize Mars? This was a general question. What are the conditions in Mars which is favorable and to be modified for a Mars colonization?
So the most important problem about living on Mars is the radiation. So there are you can't really walk out on the surface and you will be hit by hard radiation which a human being cannot survive. So always one would have to be enveloped with enough oxygen. Like you saw in the slide, Mars is mostly carbon dioxide. So it will be a challenge, but then I'm sure people will overcome the challenge. There'll be a lot of solutions. So by far, colonizing on Mars, one of the important things is how do you take care of the radiation all around. And of course, the gravity is another thing, but then radiation, I think, would be the toughest thing to handle. Yeah, so you're asking if it is possible. Yes, you have heard, no, right? Elon Musk has said that he will put a man and he'll try to colonize.
Okay, ma'am. The next question was the gravity of Mars is less than that of the Earth.
Yeah.
What problems that are
About
going to
38%, yeah, maybe 38% of the Earth, yeah.
then what are the problems faced by humans in colonizing Mars?
Yeah, but I'm sure these all these aspects can be really taken care of. See, people are surviving in the ISS, right? People are living in space for years together. So there will be methods and mechanisms to survive. I'm sure the technology will evolve.
Okay, ma'am.
You have
Thank
seen
you.
how people live in the ISS, isn't it? Yeah. Go ahead.
Okay, thank you, ma'am. It was a very nice experience for me and all the other participants. And thanks for answering our questions. Shajil sir, over to you.
Madam, can I ask you one thing concerning Yuvika? You are a part of that team which used to have classes and interaction with the Yuvika team. Yuvika,
Yuvika, sir.
that ISRO's student program. That was only one batch is over. Second batch last year could not be done because of the COVID. Every state has two students.
Yeah, I have. I really don't remember if I've given a lecture for Yuvika because
Okay. Because one of our boys got selected last year for Yuvika. Out of two from Kerala, one was he in our UL Space Club. But unfortunately, COVID didn't enable it to happen. Okay, I only wanted to check with you whether.
no, I'm not a part of Yuvika, sir, right now.
Okay. Because your talent and skill in in imparting the knowledge is adapted to school students is fantastic. The way you are delivering to our boys and girls, it's something very extraordinary. That is why I wanted to ask you. Okay, thank you.
So may I ask a question?
Yes,
Yes.
sir.
Sir, may I ask a question?
Please, sir. Go ahead,
I
sir.
want one clarification, Nandini. I just want to understand because some information for us, who are outside ISRO retired people, we don't get full information. That's why this is an opportunity to know about Mangalyaan only. I
But
just
sir,
want to know whether
but
there
sir,
have
but sir,
Ah,
but sir, Guru doesn't need a permission from the Shishya
That's
for asking a question. Vice
there is no
versa may be true.
there is no Guru Shishya here, sir. She has done so much in mission. So my question is, Mangalyaan mission after the uh, um, orbit insertion and the initial certain operations of certain changes required in orbit and some orbit maneuvers may be which would have been required for siding spring observation and all that. After that, has there been any requirement? What can be the requirement of orbit maneuvers and what kind of fuel consumption is happening?
So what happened was basically the like you said, after the initial orbit we had not envisaged any maneuvers at all, because we were not doing any ground track control or maintenance.
Oh, yeah, right.
And but what happened was 2 years after the mission, the spacecraft was encountering a long eclipse. In our design, when we worked out, we had worked out an eclipse of 90 minutes, and the battery could survive only a 90 minutes eclipse. Beyond that, it would have died. But what we found was we had a very, very long eclipse of 8 hours after 2 years of mission life. So then, when this was found in the simulations, there were a lot of schemes on how to avoid this 8 hour long eclipse. And we took a very drastic decision to do an out of plane correction, change the plane of the satellite so that it escapes that long eclipse, basically to avoid that eclipse geometry. So there was a considerable amount of fuel spent for that. But luckily, the maneuver went well. But touch wood, till now we've not had any safe mode or loss of lock, wherein we have to recover using thrusters. That situation has not come, and that's how the only maneuver we did was for the eclipse, and after that the fuel is intact right now. Since whenever we need to take pictures for orientation, we are using a little bit of fuel to rotate the satellite, take pictures. So that exercise, that way we are consuming the leftover fuel now.
Thank you so much.
Thank you, ma'am. We have our honorable participant is raised his hand as Mr. Satyendra Bandari sir raised his hand to, I think it's to ask some questions. Welcome, sir.
Hello,
Okay, sir. Welcome.
I am Dr. Satyendra Bandari, and I had the same background of MPAS in ISAC long ago during Bhaskara days. So I'm very happy that things have come to such a sophisticated level, and Dr. Nandini has explained it so well. My question is about when the fuel is over and when the satellite plunges into Mars atmosphere. What are the plans? What kind of observations are planned?
So, sir, this is actually a very interesting question. A lot of brainstorming is going on now. So there is one proposal. I don't know if it's going to come through, but there is something called an aerobraking experiment, wherein when a satellite enters the atmosphere, we are able to alter the orbit of the satellite. We are thinking almost towards the end of the life, whether the structure of the satellite can undertake an aerobraking experiment. So these are just the thoughts that are going on. Of course, a lot of studies are going on by our thermal and our structures group. We have been given actions to look into it, whether the structure can withstand aerobraking, and that is one possibility towards end of life.
Yeah, besides the satellite mainframe, in terms of science, because sensors will be able to measure certain atmospheric parameters.
Yeah, right, you're right. So whatever, we are not having all the best sensors for the aerobraking experiment, but whatever we have, we can get some information with the available sensors. So that is a thought process as of now.
Yeah, that will be great. Thank you. Thank you so much.
Welcome.
Thank you,
Nice.
Dr. Satyendra Bandari, for introducing yourself and become part of us, and welcome to our program again. Then, thank you, Nandini ma'am, for answering these questions. And next, I think it's concluding. We have reached the time. That's a 5 p.m. It's crossed now, and we have been enjoying this for 2 hours, and we are awaiting a formal vote of thanks. And before there will be a declaration of the quiz. There is a quiz already made, and the link will be posted by our students on this uh, in this forum itself, and participant can participate in it. And we will welcome all the students to participate, then attempt the concentration and on this great talk. That's information we have to the yes US Space Quiz 34 is already posted there, and it's and after that we will declare what will happen on the next second Saturday of next month. That we will hear from our founder of this UN Space Club, E.K. Kuti sir, please. Sir, please unmute your mic, sir.
Shajilmash,
Okay.
I have nothing more to add except what I already said about next session. It will be by Murali, N.S. Murali, on spacecraft mechanisms on second Saturday, 10th April at 3 p.m. So that is going to be program. In fact, Murali was there for a while as we began the program. Thank you.
Thank you, sir. Next, we come to the formal vote of thanks. Today's vote of thanks is something special because we have a girl. Her name is Nirupama Das, and we can proudly say that she was the character in that Mangalayan show that we have made. He performed as the character in the Mangalayan itself. She made her own dialogues, and he captured the attention of all the audience from the University of Calicut and Town Hall Kozhikode, and even the city of Kottayam, and even in her school. And that show is already transferred to our honorable guest Nandini ma'am yesterday. I request her to see. It's only in Malayalam. That's we are not able to give some subtitle to that, and we are thinking of that. And really, we have done a unprecedented way. We have done it, and that's only an attempt. It has its own limitation, but we have a proud girl with us. She's a gifted children. From government of Kerala has selected her, and now he's completed her 10th standard, and she's joined in government girls higher secondary school Balisheri. And I can proudly say that she is my student also, and a smart girl. And today's vote of thanks is from Miss Nirupama Das. He was acted as Mangalaya in that show. Okay, welcome. And Badsar also. Badsar, yes, we can say Badsar was eyewitness of the thing happened in University of Calicut on that day. Okay, I think he can remember that. Okay.
Shajilmash, I thought you missed mentioning it, and I was about to say that the show was viewed by PJ Bhatt and our Pappan,
Yes.
P. Padmanabhan.
Yes.
They were there with us that 2 days and a night, and we all enjoyed it together.
Thank you, sir. Welcome, Nirupama, with your switch on your video, language fluency or nothing doesn't matter. You can make a vote of thanks in your own choice. Okay, welcome, Nirupama Das.
Thank you, Shajil sir. Am I audible?
Audible, you want to make visible also. Okay, welcome. Okay.
I'm visible. Am I visible?
Yes.
Okay. Thank you, Shajil sir, for inviting me. And good evening, everyone. Today we have a wonderful session led by Mrs. Nandini Harinath on the topic Odyssey to the Red Planet. Today she shared so many interesting informations on this topic. It also felt very empowering to have a woman scientist like Nandini madam, and she's really inspiring to all of us who joined in this program. and my duty is to convey word of thanks. First, I'm conveying my thank you to Nandini ma'am for joining and giving us delivering a wonderful speech on this session. And we have our mentor Kutti sir. Thank you, Kutti sir, and moderator Shaju sir, and we have PJ Bhatt sir here, and he joined in all our space camps, and it's really a wonderful session. And I'm conveying my thanks to the students, fellows, the student coordinators, Marinatan, Sriramatan, and Ashwati, and other students. And I'm conveying my thanks to all of who were present in this session during this entire session. And thank you. Have a nice day.
Okay, thank you. You have done a great job here, and Nirupama, we are proud of you. Okay, thank you. And thank you, Nandini ma'am, for being with us. And I missed the opportunity to formally introduce you, not only because of that technical glitches, but you are in our hands, hearts, and will be ever thankful to you. And we are seeking your support to nurture these students in future. That's our humble request to you. Thank you, ma'am. Kutti sir, please unmute. Sir, you are muted, sir. Kutti sir, you are muted, sir. Muted.
Madam, Nandini madam, we have a webinar family. Those who are coming and giving a talk become a part of our family. And then we have a WhatsApp group also there. So there will be some discussions, chats, etc. And we extend an invitation every time